Hello, today I was going to be walking through how to work a little bit with AbstractGPs.jl, but primarily talking about how to plot and then maybe use the plot as intuition to figure out how we might modify. And then we can kind of see some uses of abstract GPs and how the flow might be with some custom mean and custom kernel functions. So the primary packages I'm going to use today are plots and AbstractGPs.jl. I'm using random just to kind of simulate some noise and linear algebra because we're going to use the norm function coming up, but those really aren't required for what we're going to primarily be talking about, which is how to plot and how to use abstract GPs. So we're simulating, we're going to have some true function of sine of x plus x. We're going to have some noise added to the true function output with a standard deviation of 0.05. We assume it's a normal distribution centered at 0 with a standard deviation of 0.05. We get some 4 initial samples and we have some 4 initial outputs from that function. And so we can evaluate that by just broadcasting our function to those samples. And then now we're just adding noise to simulate we had some, again, that standard deviation offset. So if we wanted to plot that, well, one of those would just be a scatter plot. So we could just scatter X samples, Y samples, and see what that kind of looks like of where those plots would be before we start trying to fit anything to it. So, okay, if you're looking at sine X plus X, you might not be able to see that, but maybe just a straight line if I'm thinking about, fitting that initially. Um, so now let's start talking about our GP. So there's a couple ways of using kernel functions or mean functions within a Gaussian process. Generally, you're going to define it by the capital G, capital P, and we'll show that in a second, with a mean function and kernel function as your 2 variables there. But one way to define a kernel function is you could use all the predefined ones on kernelfunctions.jl, and we'll pull that up at the end. But we'll start from basics where you can actually define your own custom kernel function. So you're going to define your own struct, and then it's going to be a subtype now of this abstract type of kernel functions.kernel. So of this abstract type kernel that's defined in kernel functions.jl. And if we wanted to do a exponential kernel, you could do something like this, where you have this basically says I can call it any of those instantiations of that type as a function. So that's what this syntax looks like here. And then again, the exponential kernel is the negative norm of the difference of those two numbers or vectors. The L2 norm, in this case, it's just single dimension. So just it's not too many. So the square difference, and then divide by 2, right? So this is going to be like our kernel. So if we run those 2 lines, and those are running in the REPL down there, and we can actually see like what would be the output of that kernel if I wanted to do it. So again, if I want to instantiate something from that, so I just like call my kernel, and that gives me an object of that type, my kernel up here. And now I can call it at, let's say, 2 points, let's say 3.5 and 4.0. If we can see, oh, if that's what that result would be, and you kind of verify it that way if you're looking at like experimenting or implementing your own kernels, but again, not required, but one way of doing it. So if I wanted my own mean function, so we could just be any function. So if I just said, hey, mean of x, just return 0.0, and that's just a constant function. So that would define our mean. And then so now if we define our GP, so f of x equals a Gaussian process, so capital GP, I need our mean function, and we need our kernel function. So in this case, mean is a function, and this is an instantiation of your kernel, which then you can call as a function itself. So that's why we did the syntax up here like this. So that defines our GP. Now, what do we do and how do we fit the points? So first, let's just for a helper, let's just say, well, our variance of our noise is the noise standard deviation squared, and that's just going to help us later on, so we don't have to continue worry about squaring something. In abstract GPs, it's a little odd initially, but basically you're going to tell it the GPU is defined, you're going to call it as a function and say basically prepared to receive samples of X samples and expect the output to have this noise variance of the noise. It's a little bit odd compared to other places where you might pass the samples and the posterior, but it allows some behind the scenes. So you can now call the posterior given your objective output. So if you actually wanted to evaluate what the log likelihood would be of, for example, our Y samples up here, you could actually call that now on f of x. That you told it, you basically said behind the scenes, prepare the new matrix to look like something where you receive X samples, but you don't have any Y outputs yet. So you're still looking at what the log likelihood would be of receiving anything now, just assuming you're going to get points here. So now if I wanted the posterior of that, I'm going to call it PF of x. And it's, as you'd imagine, it's probably just posterior of f of x at the points that I have. And then we have our posterior where it did all the conditioning for you, and you're now ready to use p of f of x as a function on any points you want. So if we want to plot this Gaussian process, say from like 0 to something else, well, we need to, well, what are the points we're going to plot it at? So we can just start it at 0. Let's end it at 5, and let's just step at, I don't know, 0.01. And then we want to plot it by stepping and going to the end. So if we do each one of these, now we just have discretization from 0 to 5 at 0.01. So what would, how do we pull out what the mean and variance would be there? Well, I can look at the mean and variances by calling the function mean and variance, mean and var, of our posterior at the points we want to do it at. So our posterior at the points we want to plot it at, in this case from 0 to 5 is 0.01, and we want the mean and variance at every single one of those points. So we're going to have a vector of means and a vector of variance as an output. So if we look down here and we look at mean, we can kind of see it as a 501 element vector. And same thing with vars because that's how many points we had there. So now we have mean and vars as our vectors, and now we can just use those to plot. Well, first, because we're going to get our 95% confidence interval, let's just get our standard deviations. Let's just broadcast the square root to the variances. And now we just have, instead of having to do that in the next step. So if we want to plot that, we could just do plot of what our x points are, what is our means. Sorry, I meant to do means here just so we don't override anything crazy. So means what is, so this is our x and our y. And with abstract GPs, it extends a plot function from plots.jl. So you can actually tell it to do a ribbon around the mean. And let's just do 1.96 to get our 95% confidence interval times the standard deviations. And I want to fill alpha. Let's just get 20%. I want it to be blue. Let's just make it a little thicker than normal. And I want to label it mean. All right. So this is what our points looks like. And you can imagine, all right, well, what if I wanted the other sample points on top of it? Well, kind of like before, we don't have to do this, but it's good technique to do plot equals. And then so you can come back. And when you do scatter with the bang, you can pass it plot, and then it will just overwrite or plot on top of what you already have. Let's make them red. Samples. And let's make them a little bigger so we can see what they look like. My fingers are not behaving. So now we have what our GP mean looks like with a 90% confidence interval at our points there. But how close are we to our true function? It's a little bit harder to see. So we can get y true values by broadcasting our true function. In this case, if we had access to our true function, why aren't we using it? But this is just kind of helping us debug and see what's going on there. Now we're going to plot the same thing and using the convention in the book, let's just keep it black just so it looks the same as you look at the stuffs in the book. So we can plot the true function on top of that and you kind of see like, all right, well, maybe we aren't doing too well based on maybe we need more samples. Maybe we could do better with a better mean function or a better kernel function because we can kind of see our standard deviations growing quite rapidly in between. But that is the basics. Real quick, there's another way to plot these. So before we go into messing around with the abstract GPs a little more, let's just talk a little bit about how we might be able to plot this a little differently. So another way is to use the standard deviations and get a upper bound and lower bound. So upper bound, just your means plus 1.96 of standard deviations. Again, your lower bound just minus that point. And then when you plot it, you can actually do plot the X values and just say what your lower bound is. And then for your upper bound, you're going to do fill range to your upper bound and similar kind of stuff as we did before. It's just the abstract GPs kind of fill it in for us by doing the ribbon. So this will plot the 90% confidence interval, but we still need what our mean would be. So our mean is just going to be the X plot of the mean. It's just kind of as we kind of what we started up here before, we just say without a ribbon. This just adds that 95% confidence interval aspect to it. And if we want to plot on top of that, we need to do plot with a bang. Get rid of that. You get for copying and pasting code. So that's what our mean looks like, and then our 9% confidence interval on top of it. And then similar as before, we wanted our scatter plot and the true function on top of that. We could also do that, but again, I didn't pass plot in there. So there we have. That's what we had before. So very similar to what we saw. So it's just another way of doing, just another way of plotting it without using the ribbon function. All right, so we can kind of see, let's just execute this whole thing again to make sure we don't have any errors. So this is the plot we had with some new samples. Now the question is like, well, what if I want to use a different mean or what if I want to use a different kernel? So first we're going to start off with using a different kernel. So instead of using like the standard kernel that we wrote up here, we could just redefine our own kernel and then go from there. I highly recommend it for like experience wise. Otherwise, if you go to kernelfunctions.jl and we'll bring it over here, there's a lot of built-in kernel functions that you can just pull off the shelf and use. And so the one we implemented right was the exponential kernel. We divided by two, but there's no division by two in their implementation. They just do the L2 norm. We kind of did a squared exponential basically, right? Divided by two, but there's no look, there's no scaling factor there. So one common kernel that you guys might be aware of is the matern kernel. And so you can define your kernel function. So we're just going to get rid of this part now because we can put our own stuff in here. We don't need our scatter plot to beginning anymore. So if we have a matern kernel, in this case, I'm going to define a new function saying I'm going to pass whatever value I want into it, and it's going to make it a matern. So if I want a matern, 3, 2, I would pass k of 3 divided by 2 in there. If I want a matern of 5, 2, I would do 5 divided by 2. So that's how we would access our kernel or redefine it there. So instead of my kernel, well, now we want, let's just do a 3, 2, still doing a zero mean function. And if you notice in AbstractJLs, there's actually a zero mean function that comes with it. So you don't need to define your own mean function. And we're doing the exact same thing as before. And if we plot it, this is what it looks like. So, okay. One way to kind of figure out is if you want to sample, you can kind of see, from what you expect of the continuity, is your kernel making sense? You kind of remember in the book where you see a bunch of samples from plots. Well, it turns out that AbstractGPs has a function, so you can sample from the plots. So you can sample from the function and plot it. And so basically sample from the function and plot it at these points from the posterior and give me 10 samples. And so if you run that on that, you can kind of see it overlay. And if you're expecting a smoother function, it might be like, ooh, well, this is pretty jagged. Maybe a matern 3-2 isn't the way. So 5-2 is a little smoother. So let's rerun this with a 5-2 and kind of see, okay, we see a little bit smoother of an aspect there. Another thing I want to point out is if you want the squared exponential or kind of what we talked about in class where we have some scaling factor L, you actually have to do that as a Gibbs kernel. So that's a little bit kind of a nuance. So if I wanted to define my own kernel instead of a matern kernel here. Let me replace this with, I want to define a kernel with a length scale of L. Turns out the length scale can be a function of X, but in our case, if it's just constant throughout, then we kind of get the scaling factor of L of our squared exponential. And then inside here, let's say we wanted a length scale of 2.0. So we'd rerun that again. Okay, and we can start seeing now that it's starting to condense down and a little bit more. We zoom in, smoother functions in between. One last thing is how do we put our own private mean function in? So let's say we had some intuition that it's supposed to be a sine of x, or maybe some intuition is supposed to be offset by an x or part of those for our mean function. You can kind of tell the way we did it before. We just do mean of x equals sine of x, and that'd be our mean function. Instead of doing zero mean, you just input that function. And notice it shifted it a little bit, but you might see the difference if we start getting points that are a lot further away. So let's say 10.0. Ah, I stopped at 5. Now you can start seeing instead of the mean regressing back to 0, we have some aspect of it wanting to do some sort of sinusoidal kind of offset. In this case, maybe it's not the best example. But that is the big picture on how to plot and how to interact with a custom kernel, a custom mean function with abstract GPs. The only other thing I'm going to talk about is if you want to labels and do stuff like that, a good common technique is to kind of just start off with a blank slate right at the beginning. So if we start off with something where I have my X label, Y label, everything like with my size, etc., and then all of my additional plots now are just going to be modifications to that blank slate, and it kind of just build on top of it. So you can kind of see one option of doing that as just my personal workflow that I find a little bit easier for plotting stuff. I hope you guys enjoy Project 3. If there's any questions on how to plot, feel free to reach out on Ed or send me a personal email. Otherwise, best of luck. I hope you guys have fun.